if you think about what we have learned up till now, we started the semester with dynamic programming, which is for solving LQ problems. And then later, we reviewed probability, that is for learning least squares, which is in turn for common filter. Now, LQG, what we're going to talk about today, is really a combination of what we have learned, the key concepts of what we have learned so far. So it's a combination of LQ, and you see here Gaussian. There's going to be some kind of common filter inside. The big picture is like this. The first three bullets here are what you have learned from 232. So we know if there's no noise in deterministic control design, then we can do state feedback, which is powerful in the sense we can do arbitrary pole placement for controllable systems. And if we don't have all the, so state feedback, we require the states. If we don't have all the states, we can design observers to estimate the states. To design observer, we need the system to be observable. So those are the assumptions. But the nice thing about these two is that if we design observer-based state feedback, under the controllability and observability assumptions, we have the separation principle, which is quite nice, which is saying we can design the observer eigenvalues independent from the state feedback eigenvalues. All right? Now, think about, we have mentioned this idea before. LQ is nothing but a special feedback, state feedback. It's just the optimal in the sense that is minimizing a quadratic cost function. And common filter is a special observer. It's optimal in the sense that when we have the noise term, we optimally estimate the state out of the noise. And these two combined together give us LQG, which, as you can see, as you can imagine, is similar concept of observer-based state feedback. It's just in the sense of optimized in certain metrics. So the problem definition is pretty similar to what we have done before. We have the state space system with the noise inside. And these noises are zero mean, white, Gaussian assumptions, independent zero mean, white, Gaussian random processes. Let me ask you one question. If in certain case, suppose you have a system where this noise, WK, is not Gaussian, what can you do? Suppose this W is a colored noise. It has certain type of spectral density. If W is not Gaussian, W is not white, sorry, W is not white, it's colored. And you want to do, let's say, common filter, what can you do? So you got to somehow create a massaged state space system where the noise term is white. Only if they are white, Gaussian, you can apply common filter. If it's not, you have to do some additional steps to make them white and Gaussian. Yeah, if you filtered it through a transfer function, it will be colored.
But if it's not very constant number, it's not colored.
If you scale it, it's not colored. That's the key concept. And you will learn one example in the discussion for this week. If this is not white, what will you do? Finishing up the assumptions, we're assuming x0 is a Gaussian random vector, which is independent of wk and vk, with mean and covariance matrices like this. Now we're going to do two steps to address the LQ problem. The first step is similar to two steps for LQG. And the first step is similar to LQ, where I assume I have the state. And then the second step is, if I don't have the state, what will I be able to do if I have a noise measurement of the state to do the LQG problem? I mentioned LQG is optimal in the sense of minimizing some performance index. Here is the performance index for a special type of LQG problem. It's like this. If you ignore the first part, you see inside, this is exactly in the structure of a standard LQ problem, ordinary LQ problem, if you recall. It's going to have a terminal cost and then a cost along the trajectory. And they are quadratic costs. Now, if you have the system that looks like this, well, you have the noise term. Then, question, what will be, is this term deterministic or random? If you have the noise in the system. It's random because the state is going to contain information of the noise. So this is going to contain noise information. So in that sense, if we are doing optimization along a non-deterministic cost, it's not that convenient. So what we do is we take the expectation. I have just mentioned these are containing the information of the noise, W. So take the expectation over the noise terms, W, and then over the initial condition. I mentioned the initial condition is also random. So take the expectation along this. We have this whole thing becomes deterministic. So this is one of the assumptions. And the intuition behind this is if, let's say, we do an experiment, we do it yesterday and today. Then at the end of yesterday, there's going to be some final state. And the final state is contaminated by noise. Now, when today I initialize the experiment, the initial state will be the final state of last time, which is contaminated by noise. Remember, for this special case, I'm just assuming I have all the state. Everything here is, we don't need to worry about the measurement of the state for the moment. We'll do that in a few more minutes. All right, so we'll use dynamic programming to solve this problem. And the way we define the problem is like defining this optimal cost to go, which is very similar to deterministic dynamic programming. So it's minimizing the cost at time step k is defined as the cost to go. Look at here. As the cost to go from k to n over here. And the expectation is taken over this. This is the newly defined quantity. Is taken over this noise term starting from k to n minus 1 over here. So to understand the notation a little bit more, when we say W, capital W, k plus 1, and then I'll put a plus here, this just means from wk plus 1 to wn minus 1, which is in turn wk and then capital W subscript k superscript plus. All right? So this is the notation we're going to be following. This is the noise to go, if we sort of say in the sense of cost to go. This is the noise to go, starting from time k plus 1, and this is noise to go. No, I should be k here, and then this is plus 1. Yeah. Okay, this is a noise to go at time k, and this is a noise to go at time k plus 1. Now, remember, I'm defining the cost to go as starting from time k. So when I want to minimize this quantity, I'm minimizing the control I can apply only starts from uk to un minus 1. u0 will not occur here because u0 doesn't explicitly show up in this cost function. Okay, and the notation here, again, I've been following the notation. This is the control signal, control sequence starting from time k. to time kn minus 1. Now, these are the cost to go at time k. If we think about this one, this will be the cost to go starting from W0 plus, and then the terminal cost, x transpose n s xn plus the cost along the trajectory. So if you just look at this term, can someone tell me, is this term deterministic or random? This is now getting a little tricky. The cost, the expectation over all the noises starting from time 0. Deterministic or random? Why? Mm-hmm. Those are all very true. There's one thing you are missing, one very small thing. Initial state. The initial state is also random. The expectation is taken over only the noise terms, but the initial term is still random. So the ultimate cost, optimal cost, is again considering taking the expectation over this initial state. Then this whole thing is going to be deterministic. So this is, I explained this just to let you understand why this expectation is taken in this optimal cost. Now, we're going to start using dynamic programming for solving the LQ problem with noise. So we have defined the optimal cost to go, the cost to go, k starting from k to n minus 1 to n. All right, this is defined over expectation. If you recall the last slide, it's going to be u k plus all the control signals starting from k, minimizing over all the control signals starting from k, and then the expectation of wk plus inside is going to be the terminal cost qxn plus summation of starting from k to n minus 1, and then the cost along the trajectory. Let me use j qxj plus u transpose j r uj. I'm going to use dynamic programming, and the steps here will be slightly different from the dynamic programming we did for the LQ problem. The challenge here occurs because we have now an expectation sign inside, so the steps will be slightly different, but the idea is quite similar. So first of all, I would like to connect, the ultimate goal is I would like to connect this cost to go at time k with the cost to go at time k plus 1. So the first step to do is to construct something that's going to give us the cost to go at time k plus 1. Well, we're going to need this k plus 1 term. J, Q, J, U transpose J, R, U, J. Okay? So I have taken out two terms over the summation sign. The two terms I took out are xk, q, xk plus U transpose K R U K. Now, this term is quite similar to the optimal cost to go at time K plus 1. Now, notice one thing here. Minimizing over UK, I have explained that UK here is UK in union with UK plus 1, capital UK plus 1 plus. All right? So if I'm minimizing over these two. The question, the fact that you can see is UK, the signal UK here, impact this one, but does not directly impact this term. So I can do UK, then expectation WK plus X transpose K, QXK plus U transpose K, RUK. I can put this minimize inside here, K plus 1 plus, and then the optimal cost to go plus summation from K plus 1 to M minus 1, then the cost along the trajectory. Okay? So anyone questions for this part? Because all the control signals after UK plus 1, it will not influence this first term here. It will only influence this term here. So I can put the minimization inside here. All right, I'll move on here. This term is going to be equal to, I'm going to do one more step. Minimization of UK. So this expectation sign here is the expectation over WK, small WK, and capital WK plus 1 plus. Okay? Now, one quick question is, for this WK, for this term, the noise term starting from K plus 1, will this influence this guy here? The same logic, right? So this guy does not influence over there. So I can do, write another paper. I think I need another paper, so I will write the result on this page. This equals minimization over UK, and then expectation of WK, X transpose K, QXK, U transpose K, RUK, plus, now it's a EWK plus 1 plus mean UK plus 1 plus UK plus 1, and then here inside, terminal cost plus the cost along the trajectory. So now, this term looks very much like the optimal cost to go at time K plus 1 now. We have established, the notation I used is this term equals, if you look at here, mean, oh, cannot see. This term over here equals JK plus 1, XK plus 1. If you replace every K with K plus 1 here, this term. This term is the cost to go at k plus 1. So this is, as you can see, mean uk plus 1 plus jk plus 1 xk plus 1. So if you are very careful, if you are very, very careful about the derivation, you will notice that here I switched this minimization and then this expectation sign here. I've taken out this minimization here and put this expectation afterwards. So can anyone tell me why I can do that? Minimization and expectation. I can swap the order. Noise is white. That is, even if noise is not white, I can still do this. It's independent of you. That's a very good point. That's true. And then this some additional steps. So this looks intuitively correct because expectation is for the noise and is not for you. The noise will update you. U will contain X. Mm. Mm. So what's the reason? It sounds a little bit tricky. So let me give you the one reason for that. So the fact I used is that minimization and expectation can be taken separately. For example, if I'm minimizing over U, and then inside I have the expectation, let's say over X, of a function which is updated by both X and U, then I can do one analysis. If the noise is a discrete time noise, then this expectation sign is exactly a summation of fx small x u. Then the probability mass function, this is over x. Can everyone see that? The definition of expectation. All right? So if you do that, so notice now, this summation sign is over x, and this minimization is over u. So this is now safe to do. Summation, and put this inside, minimization sign inside, f x u p x x.
The definition of u here is from u1 to un, or it's...
Oh, this is just general. Just consider this is a general function.
So here x depends on u also, because u is affecting x.
U is, let me be careful about this. X here is stochastic, and U here is deterministic. U is what we choose. Yeah.
But for example, if it's just u equals kx, k is deterministic, is a constant number, but x is random. So u should also...
In that sense, it's not exactly, what you said is it's a different situation. If U is kx, what you said is that, then we have already specified U. There's no minimization inside. When I say minimization over U, I'm given the freedom of U what to choose U. Yeah, so let's do this simple case first, and then see what's remaining for the next step. So we are here. And now you see, this minimization is taken only over U. So this equals to expectation of x, then mean of U, f xu. If I consider this term as one term, then this this thing is defining the expected value of x over this term. So that's the intuition to understand why mean and x, the expectation can be, the order can be switched. Px is the probability mass function. So summation of this times this is the exact, right? Yeah. Yeah. Coming back here, that's the logic behind this. Minimization and expectation can be taken independently. In the end, let me write down first the final result here. We have, again, by the same logic, I can switch the orders, expected value of UK, WK, and then inside is mean UK. Then now this time inside I got X transpose K, QXK, plus U transpose K, RUK, plus this term is the optimal cost to go at k plus 1. So it's JK plus 1, XK plus 1, optimal. Now this looks exactly the same structure as the deterministic dynamic programming. Okay? So take a moment to look at this equation and see it makes sense. Now, the result, I made a copy here. Probably I don't need this step. Because the reason is that if I write it in this way, mean UK, expected value of WK, and then this term inside, can someone tell me what is this term? Taking the expectation over time, over the noise, WK, and then the remaining part. Yeah, that's the J of K. And then minimization over that's going to give me the optimal. So I actually didn't need that step. So this is probably the easier way to write. Okay? Here, inside here, right? WK will not affect XK, but it will affect XK plus 1. Yeah. So let's see, somewhere here. I used a different, someone noticed I used a different notations here. I did actually this. So in the slides, I have the minimization of UK. Then I take this one, the expectation over WK, to be inside here. So I did one more step. Can someone tell me why I can do that? So which is exactly saying WK, if I take expectation over WK for this term, it's actually itself. Because, yeah, exactly, WK doesn't impact this. This term, WK will not influence XK. It will influence XK plus 1. That's why we can do that here. Okay? WK doesn't influence XK directly. It influences the next time step. So it's here. This is the final equation I want to reach. All right. This is exactly the key equation for dynamic programming. Now, the final boundary condition for this guy is going to be Jn optimal at time. This is similar to LQ problem. So it's the terminal cost over here. And then assume, this is something recall homework 1. You did something similar to this. Assume at time k plus 1, we have the optimal cost to go in this structure. It's a quadratic function of xk plus 1. So this is same term in standard LQ, plus some additional term. So this and this term will be positive. Always positive if we have noise. So the message here is that, message and the intuition here is that if we have noise in the system, then the optimal cost will be higher than the cost in an LQ problem. And why that? What is the additional cost is exactly due to the noise term, here. Okay? This is actually after we know how to do dynamic programming. But if we start from initially, we should have to go from time n to time n minus 1. And then over there, you can find this structure here. Now, this might be a little bit too small. Then at time k, the optimal cost to go, use this equation here. So substitute this cost to over here. Then I can express the optimal cost to go at time k plus 1, at time k, which is going to be the cost at time k plus the optimal cost at time k plus 1. So now, question for you guys is, this term, this whole term here, will it be a quadratic function of xk? I'm saying xk, not xk plus 1. Is it a quadratic function of xk? Is it a quadratic function of uk? Also true, right? Because xk plus 1, you see here, is a linear function of xk and uk. After you take the quadratic product here, then this will be a quadratic function of xk and uk. The message from this question is that this whole thing is going to be quadratic functions of xk and uk. And because of that, we can solve optimization over quadratic functions very easily. This is, I have to recall some result we have seen before. This is after you do the substitution of this is after you substitute the system dynamics inside here, then you will get this big chunk of terms inside. But the main message is what you have just seen. This term, this is a quadratic function of xk, and then xk, somewhere else there's an xk. Oh, I have combined the term. So the first term, the first q term from here is from here. And then this inside term is from this product here. It's from this product here. Because this is because from here to here, this is because xk plus 1 equals axk plus some additional terms. When we substitute this inside, I'm going to get xk transpose and then A transpose times P times AXK. Okay? So this is a quadratic function of xk and the quadratic function of uk. It's actually also a quadratic function of wk, but that's not the most important issue at the moment. Okay? One observation, this looks long, but one observation will immediately reduce this equation here. The observation is W is white. If W is white, can someone see that this term, if W is white, then if I take the expectation over wk, what will be this term, these two terms? Right? Because first of all, W is white, so W is independent of xk. Then if I take the expectation, I can have a separate terms of expected value of WK. So that's going to give me 0 because WK is 0 mean. And this term here, the same logic, is going to be 0 because WK is 0 mean. All right? And then another observation is this term. This term here. If I consider expected value of WK, WK transpose, the inside BW transpose P, BW, WK. Okay? So notice I have removed the UK term. I've removed the minimization over UK because this term is independent of UK. So minimization doesn't impact the result here. If I consider the expected value of this, now we have talked about the fact that EWK, this term, if I consider this part as another vector, let's say QK, then this is the trace of QK times WK transpose. So this is a fact we reviewed several lectures ago. So it equals EWK trace BW transpose PK plus 1 BW WK WK transpose. The expectation sign here is for W, so I can do trace BW transpose PK plus 1 BW, and then take expectation inside. I'm going to get capital W, which is a covariance matrix of the noise term. So a quick message is that this term, this is also intuitive. This term, this expected value of this term is a constant. This is the main message. Because it's talking about the stochastic properties of something related to the noise. So it's deterministic. It can be evaluated, and this is the result. That's the message. Now, what we have done is we don't need to worry about this term, this term, this term, this term. These we have all taken care of. And this BK term, we don't need to worry about it either because it's also deterministic. The final thing we need to worry about becomes here. We need to worry about the first few terms, that's for sure, in the expectation, in the minimization. This term, and then this term. Okay? So these terms, if you pay attention here, these terms, they don't specifically depend on WK. XK doesn't explicitly depend on WK. And all these remaining terms here. So if I take the expectation sign over WK, it's going to be just themselves. And then these remaining terms are what we talked about. They are constants. The minimization now, you see, is essentially about this simplified quadratic function here. So if you just look at this equation, can you tell me what's the optimal solution UK for this minimization problem? So I wanted to essentially bring up this slides, which we have seen before. For a quadratic function of u here, this is a quadratic function of u. Then the optimal control, if you take the partial derivative, is going to be this. It's the negative of the inverse of this matrix in the quadratic term, and then times this p vector in the linear term of u. So coming back here, what's the optimal cost? What's the optimal control? U, let's say optimal K equals, so it's going to be negative something inverse, then some other matrix, vector. What's the inverse matrix here? Exactly. So this is the way I memorize this solution here. And then what's the vector here? It's going to be it's going to be in the linear term of U. So keep in mind though, this is P transpose and this is P. So it's going to be what? B transpose, P transpose, PK plus 1, and then A XK. Okay? So it's really easy. Now you have all the... No, there's no 2 because here I have 1 divided by 2, and I don't have 1 divided by 2 here. So yeah, but it's going to cancel. So you are actually right. I'm jumping a little bit. If I get rigorous here, this M matrix should be 2 times this guy here. If I do that, I'm going to get 2 times this matrix inverse. Then, so there's going to be negative 1. So here 1 divided by 2 here, right? And then here, this is 2 inside here. This 2 cancels this 1 divided by 2. No, this here, this 1 divided by 2 cancels this. Huh? Anyone else confused about this part? Oh, I took the transpose. So this P, the P transpose is this term here, right? So the P is going to be the transpose of this term, which is this. P, huh? Huh? Oh, P, K, oh, is that here? Here, yeah, because it's symmetric. Yeah, all right? You see, using continuous, repeatedly using this fact, we can solve very complicated quadratic problems. Okay. Similarly, the full picture is the optimal cost. We have explained that optimal cost is going to be in this quadratic function of P. I think if you write it out, it's going to be for this big minimization quadratic minimization problem. The optimal cost is going to look like this. It's going to be a quadratic function of x. And then here, x. Since it makes sense here, yeah, I think it's worthwhile to dig into the details. Let's see. Here, the optimal cost is going to be a quadratic function of the P vector here. And as you have seen, the P vector is going to be related to x. So immediately you see the optimal cost is going to be a quadratic function of x. Okay? And then there's going to be a constant term q, which is going whatever that's independent of u here. And you see the result exactly over here. This is the constant term q here. Doesn't depend on u. And this inside term, this constant term that doesn't depend on u goes directly here. And this inside term is quadratic with respect to x. The structure makes perfect sense. And detailed matrices, you just have to use the equation and do some algebra to get it. Okay. Essentially, we have actually solved the problem. We just need to massage the equations to make it look nicer. The optimal cost, as you have seen, it's a quadratic function of x plus some constant term. We can define it as a quadratic function of x plus the constant. And this P matrix is whatever that's inside the whole structure here. The P matrix is going to be this one plus this one here. So if you write it out, it's a Riccati equation over here. Okay? And if you call this B, then you also see the updated equation for B, which is going to be BK equals BK plus 1 plus this term, this trace term over here. The main message is that the LQ problem with noise inside the system is going to have a Riccati equation. It's going to have a state feedback law. If you look at the optimal control law, it's going to be state feedback. You see, it's going to be state feedback. And this structure, if you pay attention, this control law is exactly the same as the control law in LQ problem. Exactly the same. And the Riccati equation here is exactly the same as the Riccati equation in LQ problem. So you see, what is different here between this problem and standard LQ problem? Yes, that's the only difference. The control law and etc. are exactly the same. The difference is just the cost has additional cost due to the noise. That's also intuitive to understand, because optimal control, we can do the best we can do. And then the remaining part is just going to be the noise term. So we have talked, as we were talking about the cost, it makes sense for us to discuss a little bit more about how the noise is, the final cost depends on the noise. And the result is here. The final optimal cost is going to be, so this is similar to a standard LQ problem. And this thing is the additional cost due to the noise terms. Pay attention here. The first term here, this is the randomness due to the initial condition, because initial state is random. And the second term here, I will first explain the result, and then I will derive why this equation makes sense. So, and the second term here, you see, is exactly due to the contributions of the state noise. So this is for noise, and this is for initial condition. So it makes perfect sense. The cost, the optimal cost in this case, is going to be the cost in standard LQ problem plus the additional cost we have to pay due to the randomness of the initial condition, and the cost due to the noise, state input noise. If you see the logic here, I'll just derive the equation over here. Derivation of this is actually not very difficult at all. The optimal cost is going to be the expected value taken over the initial condition. And the inside is this quadratic function of x plus this b term here. Now, if you do this step, if you add, consider here, if you add and subtract the mean of x over here, so I added and subtracted it over here, then you see the second term is going to be x tilde, not x tilde. Yeah, but yeah, maybe we can. So this is the difference between x and this mean value. Now, if you expand this quadratic term, you're going to get expected value of over x0 inside this x naught transpose p0 x naught plus x tilde 0, if I use my notation here, transpose p0 x tilde 0. Then there's going to be a cross product term, which is going to be 2x naught p transpose p0 times x tilde 0, then plus b0. Okay? The first term inside is deterministic. because x0 is the mean. So it's going to be x naught p0 x naught. Then the second term inside, as you can see, it's telling us the stochastic property. It's a stochastic property of x. More detailedly, it's actually expected value of x. Inside, I'm going to use my trick again. It's going to be the trace of P0 x tilde transpose. And then the third term. Can someone tell me what's the third term after taking the expectation? It's actually 0, because x tilde is 0 mean. Because x tilde, look at the definition here. What's the expected value of x tilde? It's going to be the expected value of x0 minus x naught. So it's 0 mean. So the third term is going to vanish after taking the expectation sign. This is how we derived, this is why this result makes sense. And inside here, as you can see, this guy is the trace of P0, the covariance matrix of X. So this is the result here. Why this is the trick we mentioned a few lectures ahead. A1, A2, let me do an example, B1, B2, equals the trace of B1, B2, A1, A2. I'm using this fact. So here, yeah, it's true for general vectors. Yeah. Finally, B0, if you just use this equation here, it's going to be the summation, all the summations of these terms. So it's going to be the summation of all the randomness from this dynamic update law. All right, so that's essentially, we have essentially solved the LQ with noise terms and the exactly no states. Now, think about it. The more practical situation is that we don't have perfect knowledge of the states, but we have a measurement of the states. If this happens, then the control law, instead of a function of the pure states, it's going to be explicitly about y. There may be some other terms, but the control law is an explicit function of y. So in this case, we have to consider the randomness due to this output noise. And the cost has to be modified in this sense of taking expectation not only to the initial randomness, not only to the input noise, but also to the output noise. So just the one difference here of the performance index in this case. So this is the LQG problem, linear quadratic Gaussian control problem. And the assumptions are the same. V is also Gaussian white. Just use this. So now, because of the fact that in the performance index, we have these quadratic functions of x. But we only have measurement y0 to y. We only have this measurement. Some connections has to be made. If I want to do the control using only yk here, some connection has to be made in the sense that I have to think about a way to express such a cost into some functions of y. And this is how the connection is made. It's by doing this central step over here. So we have explained that expected value of x given y. What does that equal to? Expected value of x, right? So use the same trick here. Expected value of this guy is going to be equal to expected value of this guy conditioned on yk, and then put another expectation outside. So this expectation outside the expectation is taken with respect to capital YK. And this inside is a function of the YK. So now, this is the central step. This is building us the connection. As you can see, this is building us the connection of using the output in this performance index. And detailedly, I'm just going to use a trick that I have done before. I'm going to add and subtract them. Add and subtract the optimal estimate of the state using the common filter, x hat. Then inside here, I'm going to get first a quadratic function of the difference between x and x hat, and then quadratic function of x hat, and then the cross product between these two terms. Look at this equation here. Let's see. What is, if I take the expectation over this guy, what will be the result? So keep in mind here, x hat, this expectation is taken with respect to x, because x hat is from the common filter, is the optimal state estimate. This expectation is taken with respect to x. I'll give you the hint. Yes. So the hint is this. If I take the expectation here, then I'm going to get something will occur inside here. It's going to be expected value of xk here, conditioned on yk, right? Which is x hat kk. And then it's going to cancel this term. So this is 0. Any questions? If no questions, what will be the expected value of the first term? Yeah. Then there's going to be containing some q. So the same trick. This is the trace of q times, if I use the notation x tilde k given k, x tilde, if I define this as x tilde k given k, and then this is going to be the first term here. Oh, yeah, and then conditioned on yk. Right? If you take the expected value of this guy, it's going to give us the covariance of the residual error. If we use, it's going to give us this actually. Q. Okay. So this equals Q times the notation used in common filter is ZK. Okay. So the main message I want to say is it's actually very similar to one observation before. This long equation looks scary, but inside this term is 0. This term, after taking the expected value, is a constant. The constant equals this. Huh? Oh, trace. Where is, yeah. Okay, so this guy, after taking the expected values, is going to be a constant. What's remaining, what's only going to be remaining is this term, is this quadratic term of x hat. We have started with something quadratic term about x to reach this quadratic function of x hat, where we are using the information of the output. So the main message, summarizing. So we have done all these steps. The final conclusion is that this quadratic function of x equals some constant term plus this quadratic function of x hat. If you recall, what is J? Okay, so keep this in mind. If you recall, what is the cost in LQG? The cost is the expected value of x transpose n s xn plus summation from 0 to n minus 1 x transpose j, let's say j, q xj plus uj ruj. If you recall this, then I want you to understand that now this quadratic function of x can be equivalently written as a quadratic function of x hat plus some other terms. That's the main message. And if we achieve doing that, I will claim that we will essentially solve the LQG problem. So substitute these terms inside. We can know that expected value of x transpose n s xn equals expected value of x hat n q s x n n plus some other constant term. Okay, and then do the same thing here. The result is that the original cost can be equivalently written as some constant term plus this new quadratic function of x hat, where every x has been replaced with the estimate. Now, think about it. These, as you have seen from the common filter, these depends on covariances of the x tilde, and these are independent of the control input. It comes right out of the common filter. And this is a new optimal control problem, quadratic in x and quadratic in u. Minimization now, minimization of j is equivalent to minimization of this j hat, newly defined j hat. Now, we can just focus on this j hat cost. If you recall, in standard LQ problem, we have xk plus 1 equals axk plus buk. Let me see if I'm going to use the noise. not. In standard LQ, the cost is X transpose. Yeah, maybe I still include the noise term. Standard LQ problem with noise, we have seen from a few slides earlier. We have solved this problem. We essentially have this plus U transpose J RUJ. Now, if this new cost looks like this, and if we recall the dynamics of K plus the X hat, it's going to be equal to X hat. This is the common filter equation. X hat K plus 1 slash K plus F times the error term. Which is equal to X A hat, AX hat plus B U K plus F K plus 1 E Y K plus 1. So take a moment to look at these two problems. This is the first problem, and J hat combined with this guy is the second problem. Can you see that the structures of these problems are exactly the same? You see that? The only difference is X here is replaced with X hat. Everything else, the structure looks exactly the same. Now there's one more very central observation here. In the LQ problem with noise, the assumption is WK has to be white, Gaussian. What about this thing here? White Gaussian. We have done, from the common filter we know, this is also white Gaussian. So that means the structure of the solution will be exactly the same for these two problems. Okay, so summarizing, in standard LQ problem with noise, the solution is this. Then in LQG, with this slightly different but same structure, then the solution, as you can imagine, everything else is the same. The gain of the state feedback is the same. Only difference is replace this xk with x hat k given k. Okay? And the Riccati equation is going to be exactly the same. Take a moment to think about the benefit of this result here. It's actually saying, if I want to solve the LQG optimal control problem, which is defined by several slides earlier. Let's see. Which is saying, if I want to solve this LQG problem where we don't have the exact knowledge of the state, we only can measure y, the output, and then we consider this optimal cost with respect to x. The solution is going to be, it's almost like assuming we have all the knowledge of the state and use the control law with that exact known state. Only difference is we replace the state feedback with common filter estimated state feedback. Now, if you recall what we mentioned at the beginning of the class, that state feedback and observer-based state feedback, we have the separation theorem over there, right? Now, here, you see, the beauty is that it's telling us this state feedback this Kalman filter-based observer state feedback also has the separation principle holds, meaning that we can design the Kalman filter independent of this LQ with noise kind of control law. So the two problems are separated in that sense. And this is quite nice. Okay? This is what I meant. Kalman filter is nothing but an optimal, it's a special observer. And the LQ is a special state feedback control. So the separation principle holds, meaning that the closed loop dynamics contains two separated parts, the LQ dynamics plus the Kalman filter dynamics. I'll talk about this part later, next time. And I'll finish up today's lecture with this one. So just to let you see, the LQG problem, what's the optimal cost, to let you have a quick understanding of the optimal cost in this case. So the optimal cost is going to be having the same structure using, so analogous to the LQ problem. Well, we have, this is from standard LQ problem. This is from the randomness of the initial condition. And this is from the noise for this LQ problem with exactly no states. For this LQG problem, we're going to have similarly this J optimal hat. It's going to contain, it's going to be from a standard LQ problem plus this, this from the initial condition of this Kalman filter update, and then plus this big chunk of summation here, which is going to be from the noise term, here, and the noise term here is white with covariance V plus C M C transpose. So this is a result you can review from Kalman filter. This is a white noise. Just mimicking every structure inside here to here. And the final cost in LQG is going to be these guys plus these additional terms. And as you can see, it's more involved than a standard LQ problem because of these noise terms, which we have discussed over here. Okay? Next time, we'll talk about detailing why the separation principle is beneficial.